So today we're going to start out and we're going to do a few review problems just to reinforce everything we've been learning. We're going to start out with a very simple problem. So all we're going to do is look at a negative charge. And you got to excuse my pen is acting a little funny today. I don't know why. So what distance from a negative charge of however many nanocoulombs would the electric field strength be 1.9? Now let's just review which way those field lines will be pointing. Since this is a negative charge, they'll all be pointing inwards. And again, I'm sorry that it's kind of messy there. And we're trying to find a distance where if we measured the electric field, which is actually kind of tricky, would be 1.9 times 10 to the 5th newtons per coulomb, excuse me. So in this case, we're not talking about forces. We're not talking about a test charge. We're just looking at the electric field itself. So we're going to use the E equals KQ over R squared formula. We're interested in a distance. We're interested in an R. So since we're interested in the R, let's rearrange the equation. So I'm going to multiply both sides by R squared. And then divide by the E to get that formula. I think I'm just going to leave it at this point right now. I'm not going to worry about doing the square root and the radical. We'll take care of that in a few minutes. Now it's a piece of cake. We substitute the value of K, which is 9 times 10 to the 9th. Then we put in the nanocoulombs. Now nanocoulombs is 10 to the minus 9th. And we're going to divide by the electric field strength. And we get an R value of 2.62 times 10 to the minus 4. But that's not R. I spoke wrong. That's R squared. So what we have to do then is just take the square root. And I took the liberty just to put it in centimeters. It's just easier to express it in centimeters. So that's a real basic use of the formula. To get into some more complex problems, what if we have more than 1 point charge? So now we've got 2 point charges. We've got a negative and a positive, and they're separated by 10 centimeters. And they want to know, well, what's the electric field here at this point P? Let's take a look at the field lines. I'm going to show you that on the next slide too anyway, but that's all right. We'll look at it here. This is positive. So remember, the positive person gives out from themselves. The electric field goes outward. The negative person makes it all about them, and they pull things in. So you can see these electric fields are actually adding. There's the picture. We'll call them E1 and E2. They're going in the same direction, so they're adding, just like two forces going in the same direction. You know, if I'm pushing a child on a wagon and somebody's on the other side pulling on the handle, well, we're both working in the same direction. The electric field should be pointing to the left. We might also be worth thinking about which electric field is probably going to be stronger. It's probably going to be the one from Q1. Even though this is a smaller charge, this is 25 microcoulombs and this is 50 microcoulombs, the distance here is a lot less. And just to remind ourselves, E is KQ over R squared. So the R value gets squared. So cutting down the distance really has a big effect because we're going to end up squaring that. So to get the electric field, we're going to have to add them both together. As we said, we're just going to use the standard E is KQ over R squared and see what happens here. So E1 is from the 25 microcoulomb, and that's only 2 centimeters, but I put it in meters. Remember, physics is MKS, meter, kilograms, and seconds. Oh, and I'm getting those weird spiky things there again. I don't know what I'm doing wrong. I don't know if it's my pen or my tablet. We'll see. Then to get E2, we're going to do the same thing, but E2 is a little bit further away. So it's 7.031 times 10 to the 7th newtons per coulomb. And then we can simply add them together, and they are going to add up. So that shouldn't really be a big deal. So again, they add because they're both pointing in the same direction. Now what we're going to do tomorrow, I don't think we're going to do today because it's going to take a while. Oh, we have one more thing we have to do today is let's find the acceleration. I'm sorry, there was one more thing we wanted to do. So we're saying we're going to put an electron at point P. Now let's see if we could think about it. The electron would be attracted to the positive charge because electrons are negative, and it would be repelled by that electron. So it really seems like this electron would want to move to the right. Okay, we need the mass. Well, let's see what we can figure out first. In this case, we're going to use the E is F over Q formula. We're going to try and find what the force is. But from way back, the Newton's second law, force is mass times acceleration. Now we have a couple choices here. We could find the value of force and then substitute it into ma. Or we could just take that ma and substitute it in for the force there. And that's the approach I'm going to take. And again, I apologize for the pen. I'm going to try and figure it out for tomorrow's lesson, see what I'm doing wrong. And you know me, I prefer to do the algebra first. So I multiplied both sides by q to get that q out of the denominator. And then I divided both sides by the m. Because we do the algebra first, we only have to touch the numbers once. They told us the value of E, or rather we calculated it, because we got that in the previous problem. It's an electron. The electron has that Q of 1.6 times 10 to the minus 19. That's the fundamental charge. There are no free charges in nature smaller than that. And then we were told the mass of the electron, or we could easily look it up if we wanted. And we get the acceleration. So what we did today was we reviewed working with just one charge, which we did back here. Just one charge and seeing what's going on. Then we did two charges. We found the net electric field, but it was really important to consider the arrows. And then we found the acceleration on an electron. Now, tomorrow what we're going to do is we're going to get into doing things with angles. And what do we do when we have things at an angle, and how do we use the trig? And it's a bit more involved, but we can handle it. So that's all for this video.